Okay, so if you still have any questions, I'm going to answer them, but unless you do, I will start talking about the last part that is going to be for this semester, which has these permutations and combinations. And then we're going to use those in the binomial coefficients and identities. Both of these are actually fairly easy. But anyways, we're just going to talk about them slowly and then have some exercises, some examples, so you can understand them clearly, and then yeah, we can finalize the semester inshallah with this last mini test, and that's pretty much it. Okay, so let me go back here. So we have these permutations and combinations. This is the first part we're going to do, and the binomial coefficients. So what I did actually, the slide that I shared before, I split it into two, the first part and the second part. So if I go back to the course, the resources, this is what I just did. I removed the chapter 6 that combined all of them, and I put them counting part 1 of 2 and 2 of 2. In the 1 of 2, I made the last exercises, so you can just hide the answers. If you look at the slide, it's not going to show the answers right away, especially if you run it on presentation. So this is something that I didn't do last time. I thought I did, but I didn't. So now it's fixed, and here it's hopefully it's fixed as well. Okay, so let's talk about now these permutations and combinations. So now, what are those permutations and combinations? Basically, the permutations and combinations are ways when I'd like to find a number of ways how to arrange a specific number of elements. Different number of ways how to arrange specific number of elements, and permutations is when the order, when we'd like to do these arrangements, is mattering, and when the order doesn't matter, we would like to talk then about combinations. So let me maybe start with an example that actually I took from those videos that I attached, the English ones. So I like the examples because they're simply explaining how this works. But let me just take that same example that is in the video. I'm just going to maybe expand on it because I think it might need a little bit of explanation at some point. So let's say, for example, we have like a set S of 4 elements, sorry, 3 elements, just to make it easy. Later on we'll try with 4. That's the expansion that maybe I think to do. Now, among these 4 elements, I would like to show how many, among these 4, how many 2 elements I can have that are actually going to be from these 3. How many 2 of those 3 I can have, which I'd like to have this different combination that I can have. Not combination, sorry. The combination, I'm going to use that when the order doesn't matter. So what does it mean the order doesn't matter? For example, I'd like to have 2 elements, which means I have 2 parts. The first part is going to be for the first element. Now the element can be 3, A, B, or C. That means I have 3 possible values. And the second part are the other ones. That means after taking the A, the other options that I have here are only B and C, for example. So if I take one of them, be A or B or C, what is left for the second element is just to be whatever is remaining. That means I have 2. Now this is the same thing as the product rule that we have here that we've seen last week, which actually there's 6 ways how to do that. And if we just like to see those, well, I can have, for example, A, B, and then the other thing is they have AC, then I have BC, and I'm doing that on purpose because I can also have BA. So AB or BA, that means because we said the order matters. If the order didn't matter, AB or BA are exactly the same. But when the order matters, this is where the permutation we're talking about. For the permutation, the order matters. That means the order of A and B are different from B and A. So that means I can have like B and A, and then I have B and C, right? We have this here, B and C. The other way around is going to be C and B, and then these C and A. So these are all the possibilities when the order matters. So basically I can have A and B, A and C, then I have this one A and B, A and C, then I have B and A, and B and C, then I have C and A, and C and B. So as you can see, this is 6. But again, we can solve it with the same rule that we've seen the product rule that we've seen last week, because we have like 2 elements. Each one of these, how many possibilities we have? 3 here, and how many is here? We have 2. So these are 3 times 2, that gives me 6. Now the permutation rule, which actually, let's say, it has a lot of different representations. You can find different ways how to represent those. Let's say how I have, like, you can represent them with n, how many total values that I have, and then sometimes they use k, sometimes they use r, whatever. So let's say I'm going to use k, and k is how many from these big numbers I'm going to choose. So in my case, what I did is basically p of 3, 2. That means from 3, I'm going to do 2 permutations of 2 elements out of those 3. Now there's a formula for that. So this is basically the idea behind this. Let me just go back here and just maybe skip a little bit, then I go back to those examples later on. There's a formula that allows us, like there's a theorem about the permutation, which, okay, I did not expect that. Well, it's this thing. Let me just maybe check it. I'm going to explain that differently. So they use R here in this case. So let me just use R. So instead of here the K, let me just use this control and plus plus plus. Is it? Hold on. Okay. So this here, instead of the K, I'm just going to use the same notation that they're using, which is the, what happened? I did something. I don't know what I did, but it looks interesting. R. Okay, I don't know what I did, and it's disturbing me. Okay, so anyways, I'm just going to continue like this. It looks like I'm not going to waste time. So Pn of R. So the formula is this thing over here. So that's the formula, which means if you have this permutation where you have n numbers, out of those n numbers you have R that you'd like to take from those n numbers to do the permutations with. This is the how you can the number. This is how you can calculate that. Now this thing is actually, it's actually there's a better way to represent that. I was hoping that this was the way it's going to represent, but no. So this Pn of R, Pnr. This is the actual way how it is. The formula for it, and actually this is the same as this. Now how can I show you that? Well, it's fairly easy. Let me just take this like a moment to expand on this. Now this factorial, remember, factorial is just n times n minus 1 times n minus 2, right? Times. I'm just going to reach 1 or 2 immediately. I'm just going to say all this maybe times n minus r minus 1, therefore some r, whatever the r is, plus, oops, I just would like to keep moving. Okay. Multiplied by this n minus this time r, multiplied by n minus r minus 1, sorry, plus 1, because I'm removing some r, and that r is one number before that r, and then a number after the r. That means I'm still reducing the amount until it keeps going until I reach maybe 2, and then multiply by 1, and this is the result of the factorial. Now what am I using this r for? Because actually I just would like to show that I'm going to need that. Let me zoom out. This is big too much. Let me zoom out so I can see everything. All right, so now this whole thing, this is the denominator for the numerator. For the denominator, we have this n minus r factorial, which means it's n minus r multiplied by n minus r minus 1, right? Multiplied by n minus r minus 2, multiplied by 2 by 1. Now, this is now, maybe you can see that I can do the simplification. See, for example, here, this n minus r, I have it here, so I can simplify these two. N minus r plus 1, which is this n minus r minus 1, right? And everything is going to be the 2's, the 1, etc. So what I'm left off with, I'm left out with this thing, n minus 1, n times n minus 1 times n minus 2 times etc. n minus r minus 1, which is n minus r minus 1. See, between parentheses, this is n minus r plus 1. If I remove the parentheses, is here. So this is what we get here. So actually, this is easier for me. I think it's easier to remember that this is how to find it, instead of having this kind of long representation. I personally prefer this, but if you do it, if you present it like this, that's fine. So that's pretty much the idea behind the theorem that we have, the permutations, and then we can see now, if we try to apply the same thing as what we have here, with 3 and 2, that means I have, this is 3 factorial, divided by 3 minus 2 factorial. Now 3 factorial, that means 3 times 2 times 1. 3 minus 2 factorial, that means it's 1 factorial, which is 1. And then that means you can remove this. This is equal to 3 times 2, which is our 6 that we just found already. So this is the idea behind this permutation. So far so good. So I'm just would like to introduce that. Okay, if I'm doing some kind of permutation, R permutations out of n total values, total possible values, and this is the number of permutations that I can do. But again, permutation means the order is important. Now, if the order was not important, that means for me, AB is the same as BA. I don't want to count them twice. If I'm doing the same thing now, and I would like to do the same now exercise, except that I don't care about, for me, A, B, and BA are the same. I don't want to count them twice. I'm not talking about permutation anymore. I'm talking about these combinations. Now, the combinations are when the order does not matter. And now the combinations, they have different ways how they are written. It can be like this notation or this notation, and we can use both. We'll talk about both anyways. Okay, something's not right. I think there's a bug again. So anyways, now let's go back to the same example, and I would like just to, so I can show this. Now if I go back to the same example now, and I would like to, let me, can I have some more space to work with? No, no more. Let me just increase this. All right. Okay, so let's say I'm just going to, okay, take the whole thing and move it up. So now I would like to do the same exercise, but this time I don't care about these. That means the combination, I don't want them. Now if I don't want the order, doesn't matter to me, which means for me, if I do this, that's enough. I'm not going to have these, which then what it means is that let me fix those. Okay, what I was saying is that yeah, I don't need these combinations. Now if we don't want the combinations, what is going to happen is that these are the possible combinations that I have where the order doesn't matter, which means it makes it now 3. Well, now there's a formula for that. The formula is something similar to we did. Well, basically what we have to do is this 6, I need to divide them by 2. Why? Because I have 2 ways for each one of them. Now, it's special because I have 2 different ways for each one of them, but does not, this is only specially because of this exercise when I have 3. So let's say the combination out of 3, I can choose 2 out of those 3. Now, if, oh, come on. Want to get rid of those, and there's no way for me to get rid of those. Okay, so yeah, that's the beauty of the connections. I'm trying to get rid of those, but even after removing the internet from my phone, it's still coming up. Okay, hopefully it will stop. So now, what's the formula that is going to be doing the same things? The formula is the following. Now this one is kind of interesting, but I'd like to show you actually how this works. It's similar to what we need to do. Is if I have choose r from an n, it's going to be this n factorial divided by this n minus r factorial. However, I need to divide same thing. I need to remove all the different possibilities that are repeated. So in this case, I had to divide by 2. But actually it's not 2, it's this r factorial. I'm not going to divide only by r because r factorial. Why is it that? This is actually the example that I want to expand on. I will talk about that in more details. But let's now see that this is going to give me the 3 that I did when I calculated manually and see what it gives me. Now this is going to be equal to 3 factorial divided by 3 minus 2 factorial multiplied by 2 factorial. Now this is going to be equal to 3 times 2 times 1 divided by 3 minus 2, that's 1 factorial, that means that's 1, times 2 factorial, that means times 2 times 1, which makes me simplify, and this is going to be 3. So we get the same result, but why this r factorial? And I think it's mentioned somewhere, the formula. Yes, so this is the formula. So where do we get it? This is actually what I wanted to expand on, and then I'm going to go now after that to the exercises that are in the slides, inshallah. Now to understand that, let's try to do this. Imagine now my S is not ABC, it's A, B, C, and then D. Because I want to now do the combination, to choose from these 4, I'd like to choose 3 out of those 4. Okay, now if I'd like to do this again, what I need to do is I have A, B, C, and then what is A, B, C? That's the first, and then A, B, D, and then A, C, D, A, C. I did something before the D. It's A, C, B. I'm just going to first one, second one, then the third one is going to be A, C, B, A, C, D. Okay, what else? I cannot maybe zoom out. Okay. Then I finished with A's, I'm guessing, because I checked A, B, and then C, D, and then A, C. No, I'm not done. I have A, D, and then I have B, A, D, and then C. So see, just with A, I have 1, 2, 3, 4, 5, 6 combinations starting from A. Now, starting from B, I'm going to do the same exercise. From B, I have A, C, D. Okay. And then from B, I can have A. Oh, I said D. Oh, sorry. I see. I'm choosing 3. I forgot and added this T. And BAD, that's the second one. So it's a BAC, BAD, and then I'm going to have BC, A, B, C, D, and then I'm going to have B, D, A, and then B, D, and C. I think you all agree with me at this point. I hope you're following. If you're not following, just ask a question. I just make sure that, because I'm doing this just for you to explain basically what I'm explaining. I'm trying to explain this here, this R square. Why I know factorial. Why we didn't just use R. And well, and then what is coming up next? I'm going to do the same thing. But look here. BAC or ABC, aren't they the same? So this BAC and ABC, these are the same because it's the same three elements, but the order is different. And maybe I can find some BAD and this BAD and then this ABD. That's also the same. So I'm just doing this duplication that I don't need. And then I'm going to, on top of that, I will have another duplication, which is when I'm going to have CAB, which is same thing as BAC. So it's not only by dividing by 2 is going to do. Why is that? Because the combination of the things that may have, if I have A here, and then the only two options that I have are going to be the 3 and then 2. And then if I have, again, A here, I'm still having 3 and 2 other positions that are going to be similar. So that's why what I'm going to have, all the different positions that I have for the same ABCs is going to be like 3, 2, and 1. You have these 3 ABCs too. That is the 3 factorial. So this is why, this is what we use in this R factorial when we would like to do these combinations. So that's the point I wanted to make. And yeah, so let me summarize. So what I'd like to do is, now every time I have a permutation of some number, like we use R because this is what they use in the book. So if I look at permutation, what I'm saying when I'm making a permutation, I say that the order matters to me. If the order matters, that means I'm going to use the permutation, and the permutation's formula is going to be this n square, n minus r, and I said square, sorry, n factorial, n minus r factorial. Now, if the order does not matter, I'm not doing the permutation, I'm doing the combination, and this is same formula except that I'm dividing by r square. Again, I don't know why I'm stuck with the square. By r factorial on top of that thing. So this is when the order does not matter. So this is the summary that I would like you to keep in mind, and this is what we're going to be using every time we'd like to talk about those exercises. So let's now roll back these and shift F5 and get back to those here. Okay, I cannot remove those. Okay, so let's have a look at these. So we said the permutation is set of distinct objects in an ordered arrangement. So the ordered, let's say if we have S is 1, 2, 3, the order arrangement 3, 1, 2 is the permutation of S, or blah, blah, blah. Okay, so this is permutation is the two permutations of these 3, 2, these two of them. This ABC, this is the thing that we just did. This is the example we just did. So I'm just going to do that. So you see, we can just get this 6. So I'm not going to talk about these. Let's talk about some others just to have a look. Okay, how many ways are there to select a first prize winner, a second prize winner, and a third prize winner from 100 different people who have entered the contest. Now we have 100 people that entered the contest. And among these, we would like to have 3 selected where the order of those 3 is mattering, because the first one is going to be the first prize, the second one is the second prize, and third one is the third prize. So the order matters. That's why I'm not using a combination, I'm using a permutation. And to do that, well, the way to do it is do this calculations. We said this is going to be n factorial divided by n minus r factorial. Now, which is, now I'm just going to take some space, 100 factorial divided by 97 factorial. Well, if we just think about this, this is going to be 100 times 99 times 98 times 97 factorial divided by 97 factorial, because these are easy to do. I can just simplify to these numbers over here, which is going to be this number over here. But let's say if you give me this answer on paper, let's say in the final exam, for example, I ask you this question, you give me this number, that's fine. This is enough. I don't want you to give me this one, because you can use the calculator and spend some time, and even with the calculator, if you try to do this, it's not going to work. Maybe the calculator is going to run out of memory before it can give you the 100 factorial of 100. It's going to be a huge number. If you give me also these steps, if you do it with this other version of the formula, where you do something like this, which is n times n minus 1 until times n minus r plus 1, which is n minus r plus 1, which is going to be this n minus r plus 1, which is this one over here, 98 instead of 97. So it's going to be fine as well. So let me maybe take another example. Suppose that there are 8 runners in a race. The winner receives a gold medal, the second place finishes receive the silver, and the third place receive a bronze medal. How many different ways are there to award these medals if all possible outcomes of the race can occur and there are no ties? So there are no ties, means no 2 are equal. So again, we have a permutation where the order is going to be important. Out of those 8, I need to choose 3 in different permutations. So this is going to be the different possibilities. I need to have 3 possible outcomes: the gold, the silver, and the bronze. So again, from those 8, the formula, if I try to apply it, 8 factorial, 8 minus 3 factorial, this is going to be this 8 factorial divided by 5 factorial. And I can also do the same thing, like 8 times 7 times 6 times 5 factorial, and I remove the 5 factorial, I'm left out with this. And if I have 8 people running and 3 are going to be the winners, so what are the 3 possible winners? These are 336 combinations of different winners and seconds and etc. Now these ones are where the order matters. Let's check another one where the order does not matter. Let me just do that. So for example, well, this let's see that the set 1 2 3 4, let S be this set, so we have S. Then 1 3 4 is the 3 combinations from S, not that 4 1 3 is the same 3 combination as of 1 3 4 because of the combination element. To say this, okay, I'm not trying. Okay, I'm looking for an exercise. I'm not looking for an explanation. Okay, I bought this one, poker hands. I don't want to play poker. Let's find another one. How many ways are there to select 5 players from 10-member tennis teams to make a trip to a match at another school? Okay, that's an interesting thing. So I have from 10 people, I need to choose 5, and now this is what I'm trying to do. And to do that, if I apply the formula, I cannot. It's right here. So it's 10 divided by 5, 10. Sorry, factorial divided by 5 factorial, 10 minus 5 factorial, which is 10 factorial divided by 5 factorial, 5 factorial. So this is going to be, if I do the calculations, but even if I don't, if I just stop right here, that's fine. That's the correct answer. I don't need you to go further and give me this number. This is fine. If you go further and give me this number, that's fine as well. But if in some cases it will be much hard to do that. Now, more interesting examples is when actually I have to do different combinations and multiply them because it's a product of combinations. And this is becoming more interesting. So suppose that there are 9 faculty members in the mathematics department and 11 in computer science department. How many ways are there to select a committee to develop a discrete mathematics course at a school if the committee consists of 3 faculty members from the mathematics department and 4 from the computer science department? So that means I have, out of those 9 in the math department, I need to choose 3. And out of those 11, I need to choose 4. So that means what I need to do is to do the combination out of those 9. I'm going to choose 3 and get the value for that. And then I'm going to multiply it by out of those 11, I choose 4. Why the multiplication? Well, because I have, like, imagine like I have like these different possibilities to choose from a math teacher, and then I need to add again the possibilities that I can choose from the other computer science teacher. So this is where I need to multiply both. It becomes like a product problem. So I hope I'm not confusing many of you, because that's pretty much all of that. So the rest is like some kind of exercises that I can let you do. I want you to try to do that. I don't want to show, okay, so I can see the result right now, but I don't want to spend too much time on that. But unless you have some questions, I can maybe explore it even further. Are you okay? I cannot hear any beeps. Am I? Because someone knows. Yeah, it looks like okay. All good. Alhamdulillah. So it's not very that difficult. All you have to do, the main difficulty, honestly, this is the main difficulty, is to memorize these two. You have to memorize them. That's how it works. So this is when you do permutations, when the order matters, and when the order does not matter, it's the same. You have to memorize one, and then you have to divide by this r factorial. And that's the way I think it's the easiest way to remember it, but you can find your own way. So permutations means order matters. Combinations mean the order does not matter. Now again, this combination can be also, sometimes you're going to see this type of syntax. Sometimes they write this from out of n you choose r, or sometimes you have this also, this n r. This is the another representation of the same thing. Okay, so if you see that, that's the same representation. I think it's mentioned somewhere. Let me see, somewhere here. So the number of r combinations of a set n is denoted by this. It's also denoted by that. So these are all also called binomial coefficients, and we'll talk about these binomial coefficients right now, because they have some kind of amazing properties that we're going to be talking about, inshallah, in just right now. So now to talk about these binomial coefficients, let's just like imagine that we're talking about some completely different stuff. And the idea is, now if we have, or maybe I can just make use of this. Let's say if someone asks you, maybe let me borrow the same example from the book, let's say, the video that I saw. Let me just maybe try to remember it. Let's say you have a plus b, let's say cube. Now if I would like to find, if I have something like this, I would like to find what are the coefficients of each one of these, or maybe let me ask you this: what's the coefficient of this a cube in this formula here, if I have something like this? Well, okay, if I'm doing like this, it's basically what I need to do is to have this a plus b multiplied by a plus b multiplied by a plus b. So what I'm going to do, I'm going to start with these two first, which is going to be a square plus ab, right, plus ba, which is again ab, plus b square, and then I need to multiply by a plus b, and this is going to be again this is going to be a cube plus, sorry, I can just make this to be actually 2ab, that will be easier. Now, that means a square plus 2ab, no, before I do that, a square times a, that's a cube, a square times b, that a square b, plus now 2ab times a, that means it's 2a square b, and then 2ab times b, that means 2ab, I clicked on something, b square, and I'm almost done because I did this one multiplied by a and by b. Now I need to have b squared times a, that means a b square plus b cube. Now can I simplify something? This is a square b. Do I have a square b here? Yeah, so that means I can have, this is a cube plus 3 a square b plus 2ab square plus 1ab square, that means 3 again ab square plus b cube. So this is for any a's and b's. The problem is, now if I'm asking you, okay, what is the coefficient of a cube, it's going to say me it's 1, right? Which is great, but what if now, if I'm asking you, it's going to be always the same, but let me just find some space and ask you this question. What is this 3x plus 2 cube? Now, my question is going to be, what is the coefficient of x cube? So coefficient means, what's the number that is going to be multiplied by x cube? So that's what I mean by coefficient. So like, for example, here, the coefficient of a square b is going to be 3. Now, if to answer this question of this coefficient, I'm trying to find the mouse to go up. So if I'm trying to do that, what I need to do is, now, again, I can do the same calculations, but also use this time to not waste my time. I know that this is going to be something like this. So what I'm going to do is maybe copy. What happened? I cannot. Okay, too many new things. Let's just do them manually. Okay, not good. Let me copy this, even though I'm going to clip. I'm going to just clip this a little bit, so go up and paste it somewhere. I'm trying to paste, okay. Come on. All right. So I'm just going to put down here so I can see now what is going to be here. This is going to be like 3x cube plus 3 times a square, which is a for me, 3x square, times b for me is 2, so times 2, plus 3 times a, what is a, 3x, b square, b, that is 2 square, plus the last one, which is b cube, 2 to the third. So now, if I could like to answer the question, which was just what is this? The whole thing I did, this whole thing just to answer the question, what is the coefficient of x cube? Now the coefficient of x cube means I need to have 3 to the cube, 3 cube x cube. That's going to be the answer. What is 3 cube? That means 3 times 3 times 3, which is 9 times 3, which is 27. So the answer is 27. Now see how much effort it took me to go to 27. There's a faster way, and surprisingly, subhanallah, the faster way is to use combinations, and this is what we're going to talk about in a few. But even if someone is courageous, he can say, oh, you know what, I'm going to do this manually every time you ask me something like this. But what if someone asks you the question Like when I have something to the power of 100, what is the coefficient of some x to be 60? X to the power of 60 is going to be what? What is the coefficient of that? Now, obviously, there's not going to be an easy way to do that. Even if you have all the courage of the world, you're not going to be able to complete that thing. So this is where the binomial expansion is going to go into effect. So what is this binomial expansion? Well, there's actually a way how to do those things. And let me just maybe try to get back into the slides and see. So you could imagine how to do that in one bigger power. This is what we're going to talk about. So before talking about this, let's have a look at these things. You have monomial, where you have this one term. Binomial, what is called binomial because it has two terms. And trinomial, three terms, etc. And the coefficients, actually these are the, again, the values that are multiplying the variables. And these are constants. So if we using those as constants anyways. So these are some sort of definitions. So every time we talk about coefficient, that means we multiply some variable with the number. And that number is the coefficient. Now, again, if we try to do this expanding a binomial manually, it's going to be easy for 0, for 1, for 2, etc. But if you have big numbers like this, now all the best. It's going to be much harder. Now the idea is that we learned that the number of R combinations from a set is denoted like this. Okay, so how do these two actually connect? So this number is also called the binomial coefficient because these numbers occur as a coefficient of expansion of the powers of such as a plus b to the power of n. Okay, I'm not seeing that. Let me just look at the theorem. Okay, let's go back to this. Now this is actually where the two are joined together because of this theorem, this binomial theorem. Now the binomial theorem is going to use this combination that we just seen lately. Remember the binomial x, the combination is when the order doesn't matter, and we know that, for example, this is going to be the same as this. C, let's say C, and then NR, which is going to be again this n factorial divided by R factorial multiplied by n minus R factorial. Now, if I'd like to know these, the binomial coefficients of every single one of those, I can. This is the theorem that I can use to find them, no matter how big the power is going to be, and I don't need to do a lot more of calculations. But let's have a look at this. What does this mean? So this is the sum of j equal to 0 to n of the combination that with the choice we choose for j from n. That means from n we choose j number. So when it's going to be 0, for example, the first time j is 0. What does, if we choose 0 from n? Okay, let's just maybe quickly just go and apply the formula. What does the formula say? N factorial divided by 0 factorial and n minus 0 factorial, which is going to be whatever this one is. This one 0 factorial is going to be 1, and this is n minus 0, that's n. That means this one, as I simplified by that one, and it's going to give me just 1. So this is going to basically give you always 1. With the 0. So I just wanted to make that sure. Also, and if I put n, let me also make sure that we understand if I need to choose n out of n. So how many different ways I can have? Well, even if I don't want to think, I just would like to apply the formula. There's going to be n minus n, that's going to be 0. That means this is 0. That's 0 factorial is going to be 1. And then I'm just dividing this by this, which gives me 1. So this one is equal to 1. This one is equal to 1. Now these ones are the ones that I need to calculate, the ones in the middle. Now the ones in the middle, they follow this pattern. Now what's the pattern? So that's the pattern. Now depending on what kind of, which coefficient you want, you just need to tell me what coefficient you want, and then I can just know what is going to be the, I was saying which coefficient, I mean which variable you want me to track, and then I'm just going to tell you what's the coefficient of that variable. So this is the basic idea. So let's have a look at this and try to understand it. So we have this combination. This is going to be the coefficient, and these are the variables. Now it's x to the power of n minus j, where j is going to be 0. This is going to be x of n. Why? Because x n minus 0, that's xn, multiplied by y to the power of 0. Y to the power of 0 is going to be 1. So that's why I don't have to write y to the power of 0. That's why we write this x to the power of n. And then when j is going to be 1, that's what we have here. So it's going to be x to the power of n minus 1 multiplied by y to the power of 1, which is y. And you keep going on until you find that this is n to the power of n minus 1, because n to the power of n, let me just maybe write it differently. This is x to the power of n, and j is equal to n minus 1. This is n minus 1, which is going to be, this is n minus 1. This is going to be l minus n plus 1, which is just going to be x. That's why we have x here. I'm just trying to explain how we came up with those. And then the j is n minus 1. That means that's why j is n minus 1 here. That's why the x to the power of j is going to be this n minus 1. And here, why don't we have an x? Well, because x to the power of n minus n is x to the power of 0, which is 1. So I don't need to mention that. So this is the binomial theorem. You have to memorize this. And then from this, how we can make use of that, let's have a look at this. Let's have a look. For example, if you have, I'm asking you, what is the expansion of x plus y to the power of 4? Well, you don't have to do that x plus y times x, you do it manually one by one. All you have to do, you can just make use of this formula, and then you can get it. Or the sum, like this shorter way to do it. So it's the sum of j is equal to 0 to 4, with the combination from choose j from 4 and x to the 4 minus j 2 times y, and then just distribute that and make the j become 0, then 1, then 2, then 3, and you'll be able to get those numbers. Now all you have to do is you can do the calculations. If you'd like to do the calculations, you can do them, but then there's a better way. If you'd like to do those calculations, this is something we're going to be talking about them, because there's an interesting pattern to find those. I can just find them quickly again with another way that I'm going to show you soon, inshallah. So again, oh yeah, we're talking about this the thing that just explained why do we have x to the power of 0, which is 1, and y to the power of 0, this is 1. So these are for the 2. So this is for the actually the part with the x to the power of 0, and this is the part when x is going the y is going to be the power of 0 for this part over here. That's why we don't have a y here. So this being said, this binomial theorem is using the combination to find the coefficient of any variable that you'd like to track. And let's now have something that is actually more, even if someone is courageous, he will never be able to do that easily, manually. So if I'm telling you, okay, what is the coefficient of x12 to the x to the power of 12 and y to the power of 13 in the expansion of this x plus y to the power of 25? Well, all the best. Now, if you try to do that manually, but if you don't, all you have to do is, well, basically, you know that this is going to be the formula to apply, where my n is going to be 25. Now, j, I need to find out what j is going to make this to be 12 and this to be 13. Well, obviously, if I'm just looking at y, this is where 13, that means this j now is going to be 13. And once I know that j is 13, n minus j is going to be 25 minus 13, which is our 12, which is exactly what we want. So this shows like we're looking for something that is covered by this formula, which means now all I have to do is to calculate this to be able to know what I'm trying to find out. And this is basically, again, 25 factorial divided by 13 factorial times 25 minus 13 factorial. this is the formula for the combination or the choice out of sorry, 25. I'm choosing 13 out of 25. And this is going to be the 12 factorial. And if I'd like to do the calculation, I could, or maybe I can try to simplify, but this is going to be enough as an answer. This, if I'm asking you this, if you give me that answer, that will be enough. You don't need to calculate that. You could if you want to, but you don't have to. And this is the idea, basically. This is the answer that I'm looking for. This is going to be the coefficient of x to the power of 12 times y of the power of 13 if we do this expansion. Now, if we now do these, now if we look at the same thing, the coefficient for x12 and y13, when we have something like this. Now it's not only x plus y, because you remember the formula is about x plus y that has this thing. Now if I'd like to apply this formula, I need to slightly do something different. Why? Because I need to convert this to something that looks like some x plus some y. So that's why you see this x, no problem. I'm having 2x, or this can be a, for example. You can replace this x with a and b, so it'd be easier. Now my a is going to be equal to 2x. What about my b? My b is minus 3y. Then a plus b is going to be 2x plus minus 3y, which is going to be 2x minus 3y. So that's basically, from here I'm going to make some changes to find myself that I can still apply this formula. And then once I have that, just all I need to do is to make changes to this x now include 2x, and y is not going to be minus 3y, and the same thing applies, and I get the same result. The same type of, apply the same type of formula and get the same result. And that's the coefficient of x to the power of 12 and y to the power of 13. So this works with any type of binomial expression. Now the even better way to find, but not easy when you have this anyways, these big numbers, but if you have a smaller number, there is actually there is an easy way, which is how to find those coefficients, and this is called the Pascal's identity. Now Pascal's identity, before going further into how these things over here, I just won't like to go, it's just look at this. There's this guy who found out that there's kind of an interesting property if you just start building some kind of triangle where you start with 1, and then below that one, you just, every time in any new line, you just put the 1 plus 1. I mean, the sides are going to be always 1 at the end. However, for all the others, this is going to be, because the others, they're going to be every time you have actually just one part, you just make a 1. Now in those ones, it has like some kind of like two immediate or above them parents. All you have to do is to add these two, and then you get that. So this, let's have a look at this property. Every time you have, like for example, this 3 over here is because it's 2 plus 1. Why this one here stays as 1? Because I have this one and then there's nothing. You can look at it as 0. It's going to be the same. So now if we look at this principle, every one, if you look at these two, is going to be the sum, is going to give you that 3. This one, well, there's nothing. Look at it like 0 plus 1 gives you this one. So if you just follow this type of principle, you take up any one. This 10 is going to be like this 6 plus 4, and this 10 is going to be again 6 plus 4, and this is 5, which is 4 plus 1. This is nothing because there's a 0 here, so it's going to be stable. So these kind of numbers are kind of amazing. So this guy, when he did this, he found out, oh, it's interesting. Now look at this. If I have a plus b to the power of 0, what is the answer? It's 1. What about a plus b to the power of 1? What are the coefficients? I have a plus b. Coefficient for a is 1, coefficient of b is 1. Interesting. Okay, a plus b square, which is going to be a square plus 2ab plus b square. This is for the a square, this is for the ab, this is for the b square. And you keep going on. If you have cube, a plus b cube, these are going to be the coefficients that of this thing that we just said. Now, if we try to follow the same thing with the same order, these are going to be the coefficients that I can just find just by build them. If, for example, I'm asking you, okay, give me for this is for n equal to 0, n is equal to 1, 2, 3, 4, 5, 6. Now, if I ask you, okay, for a plus b to the power of 6, what is the coefficient of a to the power of 6? Well, basically, just going to take the first one. But what about, okay, the next one? What is going to be the second number that comes after a to the power of 6? Is going to be what? According to the formula, let me just again bring the formula. The next one is going to be the n is going to be minus 1, and then y, which is n minus 1 in my case, is going to be a 5 and then times b. Okay, what's the coefficient? I can find it kind of easily. I don't need to calculate that. If you want to calculate that, you're going to find it. I can calculate that actually. Remember this, I can use that, which is out of 6, I choose 1. Right? Because remember, this is also this one over here. J is going to be 0 for the first one, and then j is going to be 1 for the second. So that means it's going to be 1. So what is the combination 1 out of 6? Again, it's 6 factorial times 1 factorial. 6 minus 1 factorial, which is going to be 5 factorial, which is going to be, this is equal to 6 times 5 factorial divided by 5 factorial, which is going to be the 6. This number over here. So this Pascal's identity is kind of an interesting property that is going to allow me to add these two numbers from the previous line that I found to find the next one. Now, how to formulate that? That's how to formulate that. So this is like the way that I'm going to be formulating this. And this is the, remember, this here is the result of the combination. So if I'm looking, I'm assuming that this is n plus 1. So if I'm looking at some number here, so the combination of this n plus 1 k, whatever that k is going to be the number of the elements that I'm looking for. So this is 1, 2, 3, etc. This is the k, and this is the n, which is the line I'm in. This n plus 1 is going to be this n, which is the line before, with this k minus 1, and then the k. K minus 1 is this one. So if you just okay, let's have a look at these. What k in this case is going to be. K is going to be from 0 to whatever n is. So let's try to find out with maybe an example. I don't know if I have an example. Yeah, this one over here. So let's say this is 0, 1, 2, 3. This is where this is the k, and this is the k again. 0, 1, 2, 3, 4, 5, etc. So now here, this is my n. This is my n plus 1. So if you look at this here, this is n is equal to 6, and k minus 1 is 4. That means this is 6. Let me just write 6 here. And k minus 1, that means it's 5 minus 1. I'm just going to write like this. So because I have this 4. This one plus 6, 5, that means this 6, it is my n. I said n is 6. And then we said k is going to be 5. That's why I have 5 minus 1 gives me this 4 over here. Let me remove that. It becomes not readable. So this first part is this one, and this second part is this one, 6k. K for me is 5. So this is going to be equal to what? To this number over here, which is this k plus 1, because I have this 7, see, k plus 1, which is 6 plus 1. Sorry, n plus 1. I'm trying to confuse you. 6 plus 1, and here this is the same k. So basically this here, all it means is that for every line of this Pascal triangle, you just go to the ones that are above it, you sum them up, and then you get this number over here. And this is how this is mathematically formulated. Now let's have a look at maybe some kind of examples. Do we have? Okay, let's have a look at this. Expand this 3x minus 1 to the power of 5 by using Pascal's triangle. Now, what I have to do this is I need to look at the power. The power is 5, and it says I'm looking at the 5th row. This is actually a mistake. This is not the 5th row, because the first one is, unless you don't consider this one the first row. This is the first one, the second, the third, the fourth. This is the 5th, and this is the 6th one. Now, if this is the one that has for the power of 5, because this is power of 0, power of 1, power of 2, 3. This is for the power of 4. This is for the power of 5. So this is not the 5th line, is the 6th, because we start from 0. So this actually should be corrected. I did not pay attention to it. So the sixth row of the triangle is going to be this one over here. So these are the coefficients of this, using the Pascal's triangle, of that thing. So if I would like now to expand that, this is going to be 3x, sorry, not 3x, this is 3 to the power of 5. So it's 3 to the power of 5 x5 times 1. So this is the coefficient out of this. Now remember, this a works with the a plus b to the power of 5. So now if I'm using this 3x in my a, I just need to have my, instead of having like 1 times a to the power of 5, my a is 3x. That means it's going to be 1 times 3x to the power of 5, which is going to be equal to 1 times 3 to the power of 5 x to the power of 5. So this is why I'm saying that this is the 3. Let me just erase everything. So this is why I'm saying if this 3x, if I use for the first one, this is going to be 3 to the power of 5 times x to the power of 5, and then plus 5. I'm going to have again 3x to the power of 4 times minus 1, because again this is going to be b. 3x is my a, minus 1 is my b. At the end I have a plus b, so that's why I have something like this. So this is going to be minus 1, and this is power of 4. It's not really clear now, but this is 4, and this is the multiplication. So now that means this is 3 to the power of 4 times 5, and then it's going to be negative, because I'm multiplying by minus 1. So that's basically the idea that is written here. You see, this is the 1 that I'm getting from here, and 3x to the power of 5, and this is minus 1 to the power of 0. I did not put it because to the power of 0 this becomes 1. I don't have it. But here in the next one I will have this 5, which is this one over here, with 3x to the power of 4 multiplied by minus 1 to the power of 1, which is going to be minus 1. And then again I have then 10 multiplied by 3x to the power of 3 minus 1 to the power of 2. So this becomes positive. So I can just remove this, because this becomes like 1. Minus 1 plus 1 minus 1 plus 1. This is what is going to be at the end. So then if you just keep going, you're going to be able to have this formula. If you just do the calculations with the powers, etc., This is going to be the first one. The next one is the negative, then the positive, then the negative, then the positive. Then it's going to be negative, because minus 1 to the power of 5 is going to be a negative number. So this allows me to, without doing a lot of expansion myself, I can use the triangle to find those coefficients, and it makes our life easy. But it was an interesting discovery that was made by this guy named Pascal. And that's pretty much it about this. But I don't know if you're oddly quiet today. Oh, because that's Maghrib. Oh, subhanAllah, time is kind of running. Okay, do you have any questions? Is that clear, or anything is you want to ask question about? It's all good. You just want to get this over with and move on. Okay, now I have this mini test 9. In the next lecture